North Carolina. Like,
yeah, if you're outside UK and you Google Durham, you'll get the North Carolina.
okay.
Yeah.
Which is presumably named after this one, right?
Of course.
All right. So our next talk will be by Gabriel Cuomo. He'll be telling us about charge spinning operators in CFTs. Please.
Okay. So, okay. Thank you so much for allowing me to talk and the organizers for the wonderful workshop. Today I'm going to talk about some work which is actually a bit old, done with 12 years ago, done with collaborator Di Piffero, Antonio Fuentes, Shamoni, Del Piscari, Claudio Tazzi, and work in progress with Zorko Margowski, which is yet to appear. Okay, so to put this work in context, there's been a huge effort towards understanding properties of CFTs in general, especially in non-perturbative regime, from the bootstrap perspective, many other perspectives. And something that now people understand is that there are certain regimes of CFTs, irrespective of how strongly coupled they are, that can be addressed via semi-classical methods. One of these is the large spin regime, so correlators made of operators with large angular momentum, admit some kind of analytic description, first in terms of semi-classics and then formalized by the bootstrap. Relevant for today will also be the regime of large internal charge under the internal symmetries of the theory. And finally, there is some sort of semi-classics, as maybe is expected from holography, which emerges in the regime of large screen dimension. I think this is related to what Julian talked about at the beginning. So the picture underlying all this understanding is the same, I think, in the three cases. It is the idea that in CFTs, observables are correlation function of local operators, at least the basic observables. But local operators correspond by the state operator map to states for the theory quantized on the cylinder. And by the way, I'll be talking about CFTs in dimension larger than 2 almost today, so no Villach solve, or 1 plus 1. So once you have a state, especially in a compact manifold, so like the sphere, you can try to expect some kind of simplified or semi-classical description when you have large quantum numbers. Like we are using quantum mechanics, for instance, the hydrogen atom becomes semi-classical in the regime of large angular momentum. So we can expect something like this here. Okay, so I think the oldest example of where this logic was successfully applied is the case of large spin operators. So, for instance, you can imagine you have some operator phi in your theory, and then you can ask if there's something which looks like phi, many derivatives phi. So these are large spin data. Okay, at large n we know it exists, but you can try to make sense of this also beyond large n, indeed use this idea. And then understand and suggest, okay, such an operator should be described by the dual state by some particle spinning on the cylinder very fast, like almost at the speed of light, because they're larger than light. And by using this description, they said, okay, to leading order, you can predict the energy of this state, which is nothing but the scale dimension of the operator, and to leading order is some energy of free particles, plus some subleading corrections, which turn out to be suppressed by inverse powers of the angular momentum. I'm not going to review that, but the basic point is here we have a very sharp prediction for the scale dimension of this operator, even if the theory is strongly coupled. And this result, remarkably, has been rigorously established by the analytic bootstrap in the subsequent years and as the heart of the Regge theory in CFTs. Okay, so this is very general, but today I want to ask a very concrete question. So I want to focus on the critical point of the U1 Landau-Ginzburg theory in CFT. So you take our famous favorite lambda phi 4 theory, you go to the critical point, this belongs to a CFT, which is the O2 CFT in 3 dimension. It's a strongly coupled theory. It's hard to make prediction. And we call the lowest dimensional operator the given charge or spin OQJ. So this could be phi and derivatives thereof in the simplest formulation. So the question I want to ask is, what can I say about the scaling dimension of this operator for this theory? And so we have tons of results when Q and J are further 1 from the numerical bootstrap. I think the latest one and most precise one in this paper. It's harder to address regimes where quantum numbers become parametrically large from the numerical bootstrap. but we can use semi-classics in that regime. At least we can expect that semi-classics should help us. So the starting point of this talk, so I'm going to read it a bit more in detail, is that we actually know the answer into the opposite regimes. The regime of J to infinity and fixed charge is a picture like the one I showed before. You expect the operator to be schematically given by a bunch of phi's separated by a maximum amount of derivatives, somewhat symmetrically distributed. So of course it's just a picture, but this really means that the state is made of q approximate free particles, and therefore the energy is just given by the orbital angular momentum plus q times the energy of the single particle plus 4 actions. And this is a prediction for the scale dimension. So it's just a generalization of the diamond descent. Q is the theory as a U1 symmetry.
Okay.
So Q is the charge under the U1 symmetry, and you can schematically think as the number of phi's in your operator.
Okay, but why that writing? Oh, J over Q is the total number.
Yeah,
Q over Q
it's
times-
schematic. This may not be an integer. You may also imagine if derivatives may be distributed in a different ways. It's a very schematic writing, but this
Okay.
prediction here is solid.
So J derivatives Q fields.
Yes, somewhat like this. The opposite regime is the regime where the charge is much larger than 1 and J is equal to 1. And we expect this regime to be described by a superfluid phase. I'm going to explain what this means, but it just physically means that the state created by this operator on the cylinder should be some sort of superfluid state. And this is, again, a prediction, which is that scale dimension goes like Q to S3R. This may seem not obvious because you have Q operators, you might expect it to be linear in Q. But actually, again, superfluid phase, there are coherence effects, it's a non-trivial phase, and this happens to be the prediction. And
Sorry,
but-
you are in the superfluid. What do you mean by superfluid?
I'm going to explain. Now, this is a local operator in the vacuum.
Yeah.
This local operator in the vacuum creates a state for the T on the cylinder. And I'm going to argue that the effective field theory describing this state is the one of a superfluid in some sense. So
So
it's,
you act on a CFT vacuum.
Yes.
And then you get a superfluid
yes,
state.
yes. So so this is one of the very non-trivial things is that actually I'm studying local operators, but they correspond to states, and then I can guess what this state is. By the way, this Q2SC alpha is by now fairly well verified with Monte Carlo simulations, so it's not fiction. So this talk will mostly be a review of this result, but what I hope to at least show is that actually we now know more than this result. We know what are the description or the prediction in the regime where both Q and J are large, and now this regime interpolates to this regime some kind of smoothly using these ideas. So are these statements clear, or the questions clear?
So in a Gaussian theory, that would be proportional.
In a Gaussian theory, this would be exactly due. So this is very non-trivial that you have interactions here. Yes, so that's why it's non-trivial. Okay, so let me start with the review.
Was the 3/2 particular to this model or any?
Well, Q alpha actually follows based on dimensional analysis. It's for any 3D CFT, large charge states, unless you have some symmetries, specific symmetry like supersymmetry, the scale dimension should go like Q3 alpha. I should say. Let me explain this argument here, and I'm going to come back to your question. So let me consider the state, the operator with spin equals 0, which is some operator phi to the Q, and it's some state Q for the theory quantized on the cylinder. Now, spatial manifold is a sphere, so it's finite volume. And I can call R the radius of the sphere. So this state has some finite charge density, Q over R squared. And when Q is large, this is much larger than the volume, than the inverse volume of the sphere. So there is a parametric separation between the scale set by the charge density and the compactification scale of the CFT. So a state with large charge density is in some sense a sort of condense matrix state. And now we are led to ask which one. So even before asking which one, I want to ask for Tim's question. So the idea is that once you have such a situation, you have a scale which is much larger than 1 over R. So you can use dimensional analysis. The energy density is dimension 3, and the charge density is dimension 2. So the most natural relation is that energy density goes like charge density to power 3r, just by matching dimension. And this is what you expect of a smooth microscopic limit. So in the infinite volume limit is what you expect. Is it clear, the argument? Maybe not. Okay, I'm trying to say. So rho at dimension 2 sets a scale like mu square, which is q over r square. And the energy density at dimension 3. So you expect this to go like mu cube by dimensional analysis with the larger scale. And this is the q to FER. And well, the integration over the volume doesn't matter because it's finite. So any generic state should obey this relation. Supersymmetry theory or non-generic and some might evaluate. So which state should correspond to this operator? Now it's a condensed matter state. Okay, you can motivate in many ways what I want to say, but basically if you look at zero temperature states where no experimental is tuning some parameter, the most generic option, and the state should be gapless because it's a CFT. So one way to see it's gapless is because you know that there are descendants on top of the state, so it cannot be gapped, the state. But the gapless states at zero temperature, the most common one are Fermi surfaces and superfluids. Now, Fermi surfaces require fermion, so I want to discuss today just a theory without fermion, so I'll assume it's a superfluid. You can motivate this by saying that on superfluid there is a U1 symmetry which is spontaneously broken, and you may expect that this happens based on some arguments, but here essentially, if you just look at these two options, the superfluid is clearly the only reasonable one for a bosonic theory.
With Chern-Simons terms, you can probably get Fermi surfaces.
Yeah, but this is operating invariant theory. No, that's a good point, but you know, this is operating invariant theory. Yes?
Well, it could be Fermi surface coupled to some emergent gauge field, right? In principles, could be some very exotic state.
Right, I'm making a genericity argument. I'm just saying I would expect exotic things to happen if there is no experimentalist tuning. You're right.
So is there like an order parameter? You said broken U1 in this state. Is there like an order parameter?
So you're at finite volume,
Yeah.
so there is no symmetry breaking. But I mean, pretty much like you can put the theory of Goldstone on finite volume.
Yeah.
So I think more than order parameter, this means that if you look at correlation functions on scales which are much smaller than the incompatification scale, the 1 over r, they behave like correlation function in a theory where there is spontaneous symmetry breaking. An alternative way of saying is that you have a path integral, there is a saddle point, you expect the saddle point to break the symmetries, and then there are some zero modes that restore the symmetry. Yes?
Maybe some statement about the 3-point function of
I think this applies for all correlation functions in the...
phi to the q.
No, I mean, there is no symmetry breaking, so correct because it's a finite volume. Correlation functions not preserve the U1 symmetry, they are just zero. But there are correlation functions which preserve the symmetry. They have a regime in distance that behave like flat space correlation function where the symmetry is broken. That's all you can say. So broken U1 would be in the infinite volume limit that I'm not taking because I'm interested in the CFT.
Maybe it's a 4-point function. Phi to the q creates the
Yes.
state, and then you do phi here.
You can do phi to the q. Sorry, 2 point. Sorry, I have 2-point function. I'm at 4-point function in the state q. 2-point function in the state q, which is a 4-point function. So it's phi to the q, phi bar to the q, for instance. Yes, sorry, you're totally right. Yes, thank you.
Why can you not take the infinite volume limits and just put the chemical potential in by hand and ask?
You can ask this question, but I think what's more striking is that this argument touches something about local operators for the theory in the vacuum. And that's also something that maybe it's easier to measure in Monte Carlo if you scale. I mean, the question I want to ask is about scaling dimension. So that's why I'm not taking it for link, but you're right, you can ask that. Okay, I already talked a bit about it, but the way as an energy physicist I think about superfluids is a theory that breaks time translations, which basically like the R direction, the U1 symmetry, and leaves unbroken a linear combination of it. That's just a way to define it. And okay, you can check this. If you are not familiar with this, you can check that this definition reproduces what you know about superfluids. And in this way, there is a unique Goldstone mode for the U1 broken symmetry, which however is expanded on an interior profile, which is linear in time. Why is that? Because if I shift time and I shift the Goldstone boson with appropriate coefficient, this profile is left invariant. So this realizes this symmetry breaking factor. And the fluctuation on top of this profile is phi. It's just a fancy way to put the chemical potential as a spinning scalar phase. Radial modes. Okay, you can have other modes in the theory, but again, genericity tells you that this will be gapped unless there is some reason for them not to be, but the largest scale of the theory, which in this case is set dynamically by the charge density, so mu. Therefore, I have an effective field theory, and I can write the theory in a derivative expansion and study the states of this theory. And this is how the effective field theory looks. So I write it in terms of chi, but remember that I should write it really in terms of the fluctuation pi. So this effective field theory starts in d to the cube, which looks non-analytic, but it's actually analytic in terms of the fluctuation once you expand around this guy. And these funny powers and coefficients of R, they are because I'm imposing that the theory should realize non-linearly the conformal symmetry group. So I cannot write the most general theory I want. I want to crucially keep track of the conformal invariant. So this is okay. For the applications I'm interested in, this is important.
R is the Ricci curvature.
R is the, yeah, I was coming to that, R is the Ricci curvature. And you can immediately power count. So the first time was like mu to the q. Mu was like square root of q. So this first time was like q to the CR. Second term was like mu times R. So it's like square root of q. And so forth so on. So the effective field theory naturally admits that the derivative expansion to the regime where the state I want to consider is large, as a large q.
What does derivative chi?
Sorry,
Yes.
yes. The chi cube means d mu chi, d mu chi. So d chi square is d mu chi, d mu chi. So,
Okay, but what is I see, sorry.
so cube is just
What is cube? But how do we contract indices?
cube is this to 3r.
Oh, I see. Okay.
So these are Lorentz invariant contractions. So we typically don't do that for condensed matter state, but this is a way to be sure that then all the nonlinear relation caused by boost and the conformal invariant starts automatically satisfied.
Is there a relation to tower of states, Anderson tower, like superfluid on a finite size?
I don't know what you're referring to, so I didn't admit my ignorance. Maybe. I mean, that people put superfluid on finite volumes before, like Son and papers, which I suspect are related to what you're saying, and they noted there are some funny things that happen for superfluids of spheres related to this. But I don't know about exactly what the thing you're referring
Like
to.
where there is, before you see the Goldstone mode, there is a tower of states which goes like angular momentum squared divided by volume.
Okay, I don't know this. You should tell me more after the talk.
Just when one does finite size diagonalization of an ordered state with broken U1 symmetry.
Maybe I can translate. Does pi have a compactification radius?
Yeah, Paka is compact. Yes.
So, in essence, yes.
Yeah, so this is chi is a compact scalar. Sorry, I should have said that because of P1 symmetry. I'm not sure why you're talking. I'm looking at a state with zero angular momentum, so I'm not sure why you're mentioning angular momentum now. I will look at angular.
I think that the cat, you're talking about these cat states, right? I think that they might actually be there.
Like if you
Mhm.
put when you study the system which is in the superfluid phase,
Yeah.
what happens is that you have a low energy spectrum on a finite system looks like integer squared divided by volume, while your Goldstone mode start at 1 over length.
Integer squared divided by volume.
But,
mean-
and that's a picture where
But sorry,
it's a rotor which is...
But in the infinite volume limit, how is this compatible with the idea of having a single Goldstone boson?
It's compatible, it's a signature of symmetry breaking in finite size. It's basically...
I mean, you're saying that they have a zero mode.
Yes.
You're saying that they have a zero mode. Yes, I have a zero mode here. Yeah, I wasn't planning to show this data. Yeah, if you contact there's a zero mode. Yeah, okay, I see now the relation. Thank you. Yeah, there is this state, which is a zero mode, and this zero mode interprets between the different values of the charges if you quantize. Yeah, so I think that's what you're saying. I think it's there, but it's not interesting for us because just amounts of changes this cube, I think. I mean, it's interesting, but it's not, I think, useful for the discussion. Is this? No, yeah.
So another question is chemical potential, right? It breaks the conformal symmetry.
Yes.
Lorentz invariant. So it's somehow conformal covariance that you're talking
Yeah,
about?
so it breaks spontaneously, not explicitly. So the system has a conformal invariance in the vacuum, right? So the state is an excitation toward the vacuum, but the dynamics are still conformal invariant.
Yes.
So this is what this action, the way of writing this action in this funny way achieves that. So like the phonon mode as an irrational moment will not be a relativistic scalar, the fluctuations. But its interaction and its sound speed will be constrained such that the theory realizes non-linearly conformal symmetry, pretty much as it realizes non-linearly with one symmetry. So it's like ghost on ghost. It's like the funny thing is that when you break space-time symmetries, you do not need additional ghost on modes besides the one for internal symmetries, typically. But that's the same way. Okay. Okay, let me just go on. But it's fine, I think. Yeah. So here I can just use this action to make now a prediction for the state with j equals 0 large charge, and this is the prediction. You recognize it as a q to the alpha as anticipated. Then there is a correction which comes from these terms. Alpha and beta are Wilson coefficients. Interesting, there is a q to the 0 term, which is not proportional to any Wilson coefficient, and it's due to quantum fluctuations. Quantum fluctuation of the phonon is essentially a Casimir energy that you can compute numerically. And it hasn't yet been verified in this model, but it has been verified in many perturbative models, which from the full theory perspective. And there are also stability corrections. So it's an FT prediction in the expansion model here. Yeah, this is maybe coming to...
Can you compute this alpha and beta?
Alpha and beta are related to this C and C1 and C2. So they are Wilson coefficients, so they are theory dependent. I cannot compute them. We believe we know C from Monte Carlo now. So alpha. I don't remember the number. So now you can expand the action, and this is how it looks in terms of fluctuation. So you see it's far from being a relativistic scalar. And okay, here I'm using Euclidean notation for some reason. And so it's a phonon mode with sound speed 1/2. And sound speed 1/2, I think, is well known in hydrodynamics. Is the sound speed that you expect for a conformal theory. So you see it coming from the expansion of the action. And the single phonon, okay, so now, okay, don't look at this formula. The point is that the phonon interpolates new states. These new states will be states with angular momentum on top of the large charge states, so other operators. And therefore you have a prediction immediately for operator with charge q and spin much smaller than square root of q, which is cut off of the theory. And it looks like this. It's the energy that I showed before, plus this term which is essentially linear in j at large j. Okay. So this is where the, yeah.
What about descendants?
Right, so the j equal 1 state, as you notice here, as plus 1. And this is a descendant. So for j equal 1, this formula predicts the energy for the descendant as not of a primary.
What about
Following j equal 1 is 2 derivatives, and so forth, so on. This is another explanation why this sound speed must be 1 out, by the way. This gets shown by that. But states with j larger than 1, Fox states with j larger than 1 is that around on your prediction. They do not follow as easily. But yeah, that's all. Okay, so I'm running out of time. I think it's fine. I think I'm just gonna flash the next thing. Okay, so this is our story, but okay, I think it's not so well. So the question is, what happens beyond this regime? Because at some point we know that this must change to interpolate with the Aldheim the Sena. And the basic idea is that, again, this is not an experimental setup really, but we can look at experiments to get intuition. So what happens if you make a superfluid spin? It's something I think all of you know. Like at some point it develops one vortex, then a few vortices, kind of Dragon Ball, then even more vortices, and eventually asymptote this vortex at this state. It's a superfluid in a trap, I should say. And so the question is, can this intuition leads us to prediction also for CFT operators? And the answer to this question is yes. Okay, so to do that you have to include vortices in the FT. Please don't look at the formula, I don't have time to explain them. But just for you, just for those of you who are educated, Yeah.
Shut your eyes.
Shut your eyes. Sorry about that. It's fine. Just for those of you who know a bit of this, compact scalar is dual to a Gauge field, U2+1, and vortices are just charged particles in terms of the Gauge field. If you've never seen this, it's fine. You can just forget about it. But the point is that you can include vortices in the FT and study states with vortices. And that's something that we did somewhat systematically with Anton and the other collaborators in the lab. And it turns out that, for instance, you have a nice prediction in the regime where the angular momentum was in this square root of Q and Q, which is just in terms of a vortex, which is spinning on the upper part of this hemisphere, and an anti-vortex spinning in the lower part of the sphere, with precisely drift motion. And this is the prediction for the scaling dimensions to leading order in JQ. This funny log, again, for those of you who know a bit about vortex physics, is just because vortices have a logarithmically divergent self-energy, as well known, and at the same time, they have a, relatedly, there is a Coulomb interaction like between vortices and anti-vortices. And this is what leads to this log. The Coulomb interaction is log into this. Again, this is just, for those of you who don't know, you just study the state and compute the energy. That's the result in hyper prediction.
What is the y-axis?
Sorry, I didn't show. So this is the sphere, and this is the stereographic projection of the sphere. So I wanted to remove it, but since the change computer, my Mathematica cannot do any more plots for some reason with color. So I had to keep it there from the old thing.
But what is, so this is some highly non-local operator which is inserting...
So I don't know how to write this operator explicitly, but it's a local operator. So all these operators are local by the state operator correspondence. A state is an operator. Now, how do I write this operator in terms of finite derivatives? It's a very great question, and I don't know how to answer it. But it's an operator with spin J.
But physically, in the XY model, the vortex insertion is in whose variables it's a non-log.
No, but I mean, it looks non-local, but it's actually a local operator because a local state. This vortex is dynamical. It's not an external defect that might be on top. I can treat the dynamics of these vortices. I mean, it's a bit mysterious, but that's why it's beautiful, because a state is really a local operator. So
Well, I do not mind inserting vortices. Just are you inserting active vortex with some separation, or what is?
Yeah, I'm inserting. This is so. Yeah, they are separated on the
Is it
sphere.
a finite separation or
Finite. Finite.
So that's the
So what-
separation on the y-axis?
Yes. So this in stereographic projection there is some separation here.
But what is the sphere? Is this a radially quantized picture?
Yes,
So your very high charge operator is in the center. It creates this superfluid state. Yes.
So the state lives on the sphere and evolves in time. So I'm looking, how does this state look like? So it's a almost homogeneous superfluid with two vortices on top, and the equation of motion of the vortices tell you that they move of this drift motion. That's again.
I guess what confuses me is that in the 3D picture, the vortex is moving, so it looks like it's describing.
In 3D, it's a bit non-trivial. If you map back to the plane, it's not about it. It's two strings in 3D if you go back to Euclidean, because of course you have to restore time. And yeah, I would have to think about it.
So it looks stringy in 3 dimensions.
Yeah, and the dimension looks more complicated, I agree. But the intuition gets simpler in these coordinates. You can repeat part of this story directly in class space, it's just a bit less intuitive. Okay, I'm running out of time, so... Okay, so let me just skim through the last two results. So the first is okay. So as I go to angular momentum much larger than Q, I should expect the state to have many vortices. Therefore, you can study this configuration pretty much as you study superfluids rotating in harmonic traps. Minimize the energy as a function of the charge and find this formula for J. And this breaks down when J becomes a further Q to the 3 up. This is the effective field theory. Essentially because vortices start spinning too fast and the effective field theory breaks. Yes?
Sorry, in what regime the vortices form a lattice?
This is the kind of lattice, the closest thing. So it's moving like a rigid body in this regime. So this is analogous to what happens in a harmonic trap. But there is never an exact lattice on the sphere.
Well,
Exact lattice is only when the frequency So in the harmonic trap, it's only when the, well, I don't know if you know what the lattice. This is pretty much like a lattice. It should be triangular, how would you say? It's not as solid in the sense that it preserves some unbroken translations, but it's a lattice. I don't know what you call lattice exactly. Maybe I'm getting this word.
I guess I think that you have to maybe match the frequency of the trap to the rotational frequency.
So when you mentioned when the frequency of the trap is equal to the rotational frequency. Okay, that never appears there because that is you have the centrifugal force that cancels the harmonic trap. That's the physics of the lattice. Here the potential is always nonlinear due to the curvature. So you never reach a point where the two things cancel. But there is still some kind of regular distribution that you can compute. So it's not exactly a lattice, it's approximately a lattice. So if you look only at the north pole, I think if you want, and then make a projection to the plane with some proper scaling, that becomes a lattice. But it's only approximate. Okay, I'm out of time, so let me just mention the last thing. I don't want to really say something good that I found out. That we found out, presumably is well known to some of you, is that there is an extra regime where you look at superfluids on the in a trap, but should be a portic trap, not quadratic. And then at some point, the lattice state becomes unstable to the formation of a ring where the fluid is purely superfluid flow inside, and there's two huge holes outside and inside. And this has been observed experimentally, like very recently. So we asked whether this state could be the last state before reaching the Diamond-Dasena picture. And that's what we find. I want to, again, just look at the picture here. This is the picture of a density of the fluid which is spinning in this direction on the sphere. So here it's all empty, here it's all empty, here where it's red is high density, then it fast drops to zero here at the edges. This state here is a soliton that we can study reliably within effective field theory in a certain regime and use to make a prediction for the scale dimension, which happens to apply between T to the 3 alpha and Q squared. And miraculously, the state starts linear in J, as predicted by the bootstrap and by the Diamond-Dasena picture. So we believe this state here, it has corrections which are different, so it's not yet the free particle state that I started at the beginning, but it gets closer. So we believe there's the last regime needed to connect the superfluid picture to the multi-trace bootstrap prediction, and we've had this result now. So I think this is a good moment to stop. And let me just summarize the result. The idea is that in the O2 model, if you look at operating with large charge and large spin, you have a series of regimes. You start from superfluid, almost homogeneous superfluid, few vortices, many vortices, giant vortex state, and eventually this free Diamond-Dasena picture. And all of these can be used to make prediction for the scale dimension. And yeah, I think that's it. Thank you a lot.
We've got a few questions during the talk, so maybe one more question.
Yes.
So there is never any kind of quantum fold.
I mean, how can you have a gap state compatible with the existence of a descendant?
Maybe there's like some commensurability between J and Q.
I wouldn't. I mean, we have something. We have some chance. You can allow for small gaps of the superfluid as long as they are very parametrically small. Like we have some picture of this in my paper with Luca Della class. We consider parity violating superfluids, and then you can add a Chern-Simons star to the action. But the coefficient should be order 1, and this, so that the gap is essentially invisible on the sphere. It's not a quantum Hall, of course.
No, but then I think in this regime, when the rotational frequency of the trap is equal to the trapping potential, people talk about the bosonic system. It's kind of like it's kind of like applying a magnetic field.
But isn't there a Churchenko mode? Isn't there the Churchenko mode in that regime? Isn't there a quadratic mode in that regime? A quadratic excitation on the vortex lattice? It's not a vortex lattice for Chernobyl. Isn't maybe I'm getting confused. I thought that the superfluid spinning at the same frequency of the harmonic trap should have a gapless mode, which is called Churchenko mode. Am I right? Nobody knows. Okay.
saying it can never happen because you can always take a derivative of the underlying CFT state, and that's the new state.
It can never be gapped.
Yeah,
Yeah, it can never be gapped. So that's for sure.
And do you understand how that mode is realized in all of these different phases? It was the phonon in the simplest one. And
Yeah, I mean, yes. In these two phases, it's still the phonon because these are kind of small perturbations.
Okay.
And here it's actually, we have kind of an almost chiral mode for the fluctuations, which are essentially intergery space. This kind of makes sense because it's a multi-trace. You can just displace derivatives around. This goes to either 1 or 2, depending on what my derivative are. So this kind of matches well, and okay, so we know how this works, yes.
Just one more question. In the picture showing the blue and the red,
Yes.
was the blue no vortices or no condensate?
So, actually, so this region, sorry, I didn't work very fast. Here there is a condensate, but there is no vortex in the condensate.
Okay.
And why it's giant voltage, you can feel the blue region, which is empty, like the giant core of the vortex.
Okay. So there's no condensate there. Okay.
There's no condensate.
There's no more questions. Let's thank Gabriel.